Machinery depends a great deal on the hydraulic transmission of power. The aim of this film is to summarize the origins and main lines of development in this important branch of technology. The Englishman Joseph Bramah was the founder of applied hydraulics or hydrostatics. He based his theory on the hydrostatic law enunciated 100 years earlier by Blaise Pascal. In 1795, he was granted a patent on what he called his hydro-mechanical engine. His specification claimed that any pressure produced by the pump could be magnified 2,034 times at the ram. This is Bramah's invention in essence. A piston pump of small diameter acts on a ram of larger diameter. Water is the hydraulic fluid. Bramah's machines were soon being used for lifting, bailing, and pressing. This one is still at work, ironing creases out of maps for the Ordnance Survey Department. Before long, steam engines, like this one at Her Majesty's Dockyard, Chatham, were harnessed to the pumps to enable heavier work to be done at higher speeds. But such engines could only deliver pressurized water at constant rates and could not deal with fluctuating loads exceeding their capacity. What was needed was a means of storing pressure, and it was not till 1851 that Sir William Armstrong solved this problem by inventing the weight-loaded accumulator. Such accumulators are still in use. They consist of cylindrical rams loaded with heavy iron weights like this one at Tower Bridge. A pump supplies fluid to force the ram upwards, thereby filling the cylinder beneath it with a reservoir of high-pressure fluid which is available to supplement the capacity of the pump. The ram remains at the top of its travel till the stored pressure is needed. Pump and accumulators combined are now powerful enough to work this hydrostatic engine which opens the bridge. As a result of this technical breakthrough, there was now no obstacle to the expansion of hydrostatic power transmission. It was used to power cranes, wagon hoists, capstans, and also to operate presses like this 1860 paper baler. The demand quickly rose to the level where it became profitable to build central pumping stations supplying pressure water through pipelines to consumers. The London Hydraulic Power Company was founded in 1882, and this station still retains its original pumping gear. Today it operates more miles of pipeline than ever before. Water is an excellent hydraulic liquid in many respects, but it has its disadvantages. It's often impossible to prevent it corroding the system, thereby choking valves with rust and scoring the rams and their packing. It forms a poor seal, and it calls for a large pump working at low revs. Here's a modern pump. It's far smaller, but runs 100 times as fast and produces pressures 20 times as great. The design of such a pump was rendered possible by the introduction of mineral oil as an hydraulic fluid. Oil does not corrode and forms a good seal. Also, it's obtainable in a range of viscosities. It doesn't freeze so easily. And it lubricates the moving surfaces inside the pumps. By the turn of the century, it was among the tools used by the great pioneers of modern hydraulics, who were seeking a compact, variable speed transmission unit. Many of their names are still famous, like those responsible for the modern piston pump: Healy-Shaw, Beecham, Towler, Williams, and Janney. And inventors of the new rotary pumps, such as Vickers, Hall, Lentz, and Pittler. And the German Fertinger, who in 1907 discovered the principle of the fluid coupling, which was to open up an entirely new field of hydraulics called hydrokinetics. But first, let's trace developments in the hydrostatic field, where hydraulic power packs such as this are fast becoming a universal tool. The design of such units is the outcome of 50 years of development in two main directions: pumps and valves. Let's first look at valves. There are hundreds of different designs of three main functions. They either control the direction, flow, or pressure of the pump, as may be seen on this press. Direction control, flow control, and critical control of pressure. Valves of all types are nowadays linked together in complex systems of control for hydraulic machines of ever-increasing sophistication. This transfer machine is completely automatic and performs a cycle of 31 separate operations on motor car crankshafts. Pressure and flow control valves ensure that each drill bores the crankshaft at the optimum speed. When the required depth of penetration has been reached, direction control valves are actuated to withdraw the drill. And this crankshaft has finished the cycle. But the heart of any hydraulic mechanism is the pump. Pumps fall into two main categories, of which the first is rotary positive displacement. There are four main types in this category, and they all work on the same principle. The traditional principle of pumping consisting of a suction stroke and a delivery stroke, except that these strokes are produced by rotary action. A chamber is created on the inlet side, which draws in liquid by vacuum. The trapped liquid is then carried round to the outlet side, where it is, of course, squeezed out as the chamber disappears. Rotary pumps differ only in the methods by which they produce these expanding and contracting chambers. First, the gear pump. Here, the disengagement of the teeth on the inlet side forms a permanently expanding chamber, sucking in oil, which is then carried round between the housing and the teeth to the outlet side. It can't get back to the inlet side because the teeth come into mesh in the center and form a seal. So it's expelled through the outlet port. The Vane pump creates its chambers by employing a circular rotor within an oval stator. In the rotor are free-moving vanes. Here's one working under a stroboscope, which produces a slow motion effect. Oil under pressure is fed to the roots of the vanes, forcing them outwards into the two narrow crescent-like chambers each side of the rotor. Let's consider the right-hand chamber. If we place an inlet port in the expanding part of it, oil will be sucked in by vacuum. And the oil is pushed out again by situating the outlet port in a contracting area. Similar to the vane is the cam rotor pump. In a sense, it's its opposite, for the stator is circular, the rotor oval, and the two vanes are housed in the stator. They act as seals between the inlet and outlet ports. So the chamber appears over the inlet port, sucking in oil and carrying it round to the outlet port. Here the oil can progress no further due to the presence of the vane, so it's pushed out. Here's a cutaway model of a screw pump. It consists of a main screw with mating top and bottom screws which act as sealing members. If we watch the left-hand end of the middle screw, we see a series of chambers forming and moving to the right. The oil is sucked into and carried along by the chambers and is discharged at the outlet end. It can't escape en route due to the seal formed by the top and bottom screws. Screw pumps are silent and free from pulsation, and are therefore suitable for jobs like the operation of submarine hydraulic gear, where, of course, silence is all important. They're used to power the rudder, the hydroplanes, even the periscope. An interesting example of the uses to which rotary pumps are put is this Viaduct inspection unit. It consists of a double-jointed boom and inspection cage mounted on a self-propelled rail wagon. The boom is operated by vane pumps and will be pushed out, down, and under the viaduct. The men in the inspection cage control all movements of the boom. They also control movement of the rail wagon along the track. This is powered by gear pumps. Rotary pumps are limited to pressures of about 2,500 pounds per square inch. This is due to the fact that in any rotary, some leakage between rotor and stator is not only unavoidable, but essential, as with no leakage there would be no lubrication. But with reciprocating piston pumps, pressures of up to 20,000 pounds per square inch are feasible. There are three reasons for this. First, being cylindrical, pistons and cylinders can be made to close tolerances. Secondly, there's one piston to one bore only, so that they can be lapped together. Thirdly, the circular section has a minimum periphery, thus leakage is kept down to a minimum. There are three types of piston pump. Their common factor is that they all use reciprocating action to make their suction and delivery strokes, but each induces this reciprocating action by different means. In the 5-plunger inline pump, it's induced by eccentric cams. Consider the pumping action in this particular cylinder. Suction strokes are achieved by springs forcing the plunger upwards as the eccentricity of the cam is reducing. Delivery strokes are achieved by an increase in the eccentricity of the cam. Thus, delivery, suction, delivery, suction. Suction, delivery, suction, delivery. Ten inline pumps drive this heavy forging press, at work on a nickel alloy billet, which will eventually become part of a gas turbine engine and have to stand up to temperatures of 800 degrees centigrade. The billet's present temperature is only 1,000 degrees centigrade, so the forge has quite a tough job. After several hours of forging and reheating, the billet has been turned into a long bar, and the forge is now engaged in final rounding operations. 3 blows every 2 seconds, accurate to the nearest 30th of an inch. The point of this operation is not only to provide the customer with a billet of the correct shape, but also to give the billet a uniform structure and the necessary exacting mechanical properties. In the axial piston pump, reciprocating action is induced by the action of the swash plate on the pistons. If the pump is fitted with an adjustable trunnion, the suction and delivery strokes can be lengthened or shortened, thus controlling the delivery rate. In this position, there is full flow. Now there's no flow. Now there's full flow in reverse. Axial piston pumps are being used to pre-stress the concrete for the Stockbury Viaduct on the new M2. The deck or future roadway is being stressed here 80 feet at a time. The petrol-driven pump fills a jack with oil, causing it to pull on the cables attached to it. These cables run through the center of the concrete and have been secured to steel plates at its far end. They'll be stretched 8 inches, then they'll be locked in position by another steel plate. Pre-stressing quadruples the strength of the concrete. Imagine that each span of this bridge was made of matchboxes placed loosely end to end. There would be no strength in it. Now imagine an elastic band passed through the matchboxes, pulled taut and locked off. A far stronger structure, of course, and this is the theory of pre-stressing. The deck of Stockbury Viaduct is only 8 inches thick. It claims to be the thinnest concrete bridge in the world. Here is a radial piston pump. Reciprocating action is induced by making the roller bearing on which the block containing the pistons is carried eccentric to the housing. This model shows how easily a radial pump can be turned into a hydraulic motor. The pump, driven at constant speed, pumps oil into a replica of itself. This forces the replica to rotate. Indeed, any rotary pump, which instead of pumping oil out of itself, has oil pumped into it, is pushed round by the oil and becomes a motor. This radial pump is of the variable delivery type. By altering the rotor's degree of eccentricity, we affect the delivery rate of the pump. Such changes affect the speed and direction of the motor. It can go backwards, or stay in neutral, or forwards. So it's a reversible drive of infinitely variable speed. Such a drive is employed to work the stabilizers of HMS Hampshire, one of the new county-class destroyers. This ship also employs a hydraulic transmission, but of a very different type. Her drive is hydrokinetic. Hydrokinetic energy depends on centrifugal force. If we rotate a bowl filled with liquid, the liquid will flow outwards and upwards. With vanes inside the bowl, this force is more positive, as the liquid is keyed to the rotating surface. This is the runner of a fluid coupling, a vaned bowl. Put it face to face with another vaned bowl, the impeller. Now bolt them together. If we cut away a section, we can see how the runner is free moving inside the impeller casing. This coupling is already filled with oil. If we rotate the impeller by a motor, it will fling its oil into the runner, and the kinetic energy of the oil will be converted into torque, causing the runner to rotate. The impeller drives the runner by causing the oil to flow in a complicated vortex, as shown by the yellow arrows. This vortex would disappear if the runner turned as fast as the impeller, and this is why it's essential for the runner to turn a little slower than the impeller in any hydrokinetic system, if torque is to be transmitted. Fluid couplings enable motors to start unloaded and develop peak torque for accelerating the driven machine. Thus, fluid couplings enable this 2,000-foot conveyor belt to start smoothly and quickly without overloading the motor. Their second advantage is that if a sudden unexpected load is applied to the motor, the impeller will not stall, but will continue to run for a period developing high torque. So should the belt become jammed, the coupling will slip till the obstruction is removed, then get the belt going again as if nothing had happened. In some types of fluid coupling, it's possible to vary the output speed, but the torque ratio will never exceed 1:1. However, if the impeller and runner have a more complicated blade structure and a third static member is introduced, it is possible to multiply torque. Now we have a runner, a static reaction member, and an impeller. In the fluid coupling, oil flowing in its vortex from runner to impeller is flowing against the direction of rotation. When the runner is rotating slowly, it's slowing down the impeller. In this diagram of a torque converter, the runner is rotating at about half the impeller speed. The oil is pushed back against the direction of rotation as it enters the slow-moving runner. But the blade design of the reaction member forces it to change direction again and flow in the direction of rotation as it re-enters the impeller, here shown by the thin, near-vertical flow lines in the middle of the picture. Thus, the impeller is being driven both by the motor and by jets of oil streaming from the runner, and torque multiplication occurs. When the runner is rotating nearly as fast as the impeller, output torque is slightly less than input, and the reaction member becomes a liability. So arrangements are made for it to freewheel. When it's revolving in this manner, it has no effect on oil flow at all, and the torque converter becomes a fluid coupling. The advantages conferred by the torque converter are obviously immense. It performs the function of a gearbox by providing a continuously variable torque ratio. This 30-ton AEC dumping truck employs 3 in series, giving a torque multiplication of 5.8, enabling it to carry its load away smoothly and efficiently. There's no need to change gear, as engine revs remain constant. As output speed decreases, so the torque increases. The dump truck also employs a hydrostatic system to dispose of its load. Combined hydrostatic, hydrokinetic machines like these are a far cry from Bramah's simple hand-operated press. Indeed, modern hydraulic units are well-nigh universal in their application. For instance, a hydraulically powered injection moulding machine can produce a baby's bath every 4 minutes. "3,000 telephones a day," or many other types of moulding, some extremely complicated in design. Scrap metal press swallows up anything from barbed wire to bedsteads. It crushes them into compact bales of steel ready to be melted down again in the furnace. This furnace is being relined automatically by a dolomite fettling machine. The dolomite is catapulted into it by being dropped onto a rapidly moving belt which is driven by a variable speed hydraulic motor. Thus, belt speed is variable, and the trajectory of the dolomite can be altered to reach any part of the furnace. Modern hydraulics even enables us to make our own waves, so that we can test models of the ships of tomorrow under completely realistic conditions. This Ferri Ferranti three-dimensional milling machine works without human aid. It's controlled by tape. It's making tailplane components for the new de Havilland Trident, and all movements of the cutting head are hydraulically operated. If you wanted to make something else, all you have to do is alter the information on the tape. It would be impossible to make such a complicated unit as this by conventional milling and routing methods. The machine turns a 1,500 pound block of aluminium alloy into a unit 1/16 of its weight by thousands of separate cuts. The unit is the constructional hub of the tailplane itself, and the tail with its three engines could be called the hub of the Trident. Where will hydraulics lead us? Its limitations decrease as its applications increase. Indeed, it's hard to think of any other method of power transmission as compact, accurate, delicately controllable, and versatile as modern hydraulics.